started. Okay, we are good to go. So 71. So that is talking about 11.5b, problem 71. We are given the function f of x equals x to the fourth minus 4x cubed plus 5. So this was in my math lab problem, so the function you got was probably a little different than this guy, but the idea will still be the same.
Yeah,
so
it was just a 10, but it was the same thing.
Okay,
Except
yeah.
for 5.
So find the absolute maximum minimum if either exists for the function on the indicated intervals. So let's write out what each of those intervals are. -1 to 2, 0 to 4, and lastly, -1 to 1. Okay, cool. So when we are looking for absolute extrema on a closed interval, we have kind of just a couple of checks to do. So one thing that we know is that absolute extrema can only occur at critical points or endpoints. So when we're looking for absolute extrema on a closed interval, that's all we look at. We don't do second derivative. We don't do a sign chart, nothing like that. All we have to do is find our critical points, take our endpoints, and then just plug everything into our function. It's actually pretty straightforward, just a lot of little steps along the way. Okay, so to find our critical points, we need to find our derivative first. So we should have 4x cubed minus 12x squared. And then one thing to note is that this derivative is never undefined. Always a good thing to note because our critical points can be where the derivative is undefined as well. And now we can just set this derivative equal to 0. Okay. Now whenever we have an expression like this with a bunch of x's in there, we want to factor wherever we can. So what can we factor out of this guy?
4x squared.
Awesome. And then what should we be left with?
So it'd be an x and then a -3, right?
Awesome. Yep. So then what does that tell us for our values of x?
So it'll be 0 and 3, because don't you just break them apart into two different expressions?
Exactly, exactly. So these are our, maybe I'll do it in another color just to have some fun. Let's say those are our critical points. Okay, and now we just go interval by interval. So -1 to 2, plugging in endpoints and critical points into our function. And we only plug in the critical points that are in the interval. So in this case, what are we only going to plug in?
Just a 0.
Just a 0, awesome. So we're going to have f of -1, f of 0, and f of 2. Okay, so looking at this function that we're given.
Now, are we plugging this into like the f of x or f prime of x?
F of x, we're plugging it in right here.
Okay.
Yep, so let me just write that out. So we're going to have -1 to the fourth minus 4, -1 cubed plus 5. And then the same thing, wasn't right, for all the other ones. 1, 2. Okay. So f of 0, that's going to be the easiest one. What'll that be?
Just 5.
Now, whenever we take a negative number to an even power, it's going to be positive.
Yeah, so that's just 1.
1, yep. And then -1 to an odd power, that will still be negative. So what are we going to have here?
That would just be 4 because it's times -4.
Yep, exactly. So +4 + 5. So this is 9 plus 1, 10. And then 2 to the 4th, you know 2 to the 4th off the top of your head?
Yeah, it's 16.
Mm-hmm. Minus 4 times 2 cubed.
Minus 32.
Mm-hmm. Plus 5. So 16 minus 32, that'll be a negative 16. Plus 5,
Yeah.
negative 11.
Okay.
So where is our max and where is our min? And actually, more specifically, what is our max and what is our min?
So our absolute min would be at 2, negative 11, right?
Mm-hmm.
And then the max would be at negative 110.
Awesome. Exactly. And that's really all we have to say.
Okay.
And then we'll go through B, but it's the exact same process. So then we have 0 to 4. And we're going to do the exact same thing. We already have our critical point, so we don't even have to do that step again. So we can just have f of 0, f of 3, and f of 4. We already calculated f of 0, so that one's done. No, that's 5.
Mm-hmm.
And then we can do this whole thing again. 5, 4 to the 4th minus 4 times 4 cubed plus 5. Okay, so really quick right here, what can we see?
There's a lot of 4s.
There is a lot of 4s. So here, this 4 cubed, that's the same thing as 4 times 4 times 4.
Oh, okay,
Right?
I see. So it's just 4 cubed minus, or 4 to the 4th minus 4 to the 4th, essentially.
Exactly, exactly. So what's going to happen there?
This 0.
Just go to 0, exactly.
And then plus 5.
So then we're just left with 5. So just some easy mental math, not having to get a calculator out at all. Okay, and then 3 to the 4th. We can rewrite this as 3 squared squared. And what's 3 squared?
Isn't it 9?
Yep, 9. And then what's
Blanking
9
it.
squared?
81.
81. So we have 81 minus 3 cubed.
27.
27. Do you know 27 times 4?
108. I just did it.
Okay, cool, yeah. And then plus 5. And then that one, we might need a calculator for that guy.
Okay.
Do that subtraction right in my head.
I got negative 22.
That follows. Oops, twice. Okay, awesome. So then now, what
I
is
got negative 22 though.
Oh yeah, negative, right. Sorry, there we go. Okay, max and min.
So min would be the negative 22 at 3, and then max would be, it would be 2 points.
It would, yep. So what we can say there, for these guys, I'll write my little arrows, is we can just say our absolute max is f of 0 equals f of 4 equals f of 5. We can just write that string of equal signs, and we're good to go there.
Okay.
Okay, and
Awesome.
since we have the time, do you want to go through C?
No, I think I got it. This is kind of the same thing.
Yep, it is the exact same thing. Well, do you have any more questions? Otherwise, I can go through some problems if you want to.
What's the difference between local min and absolute? Or I guess like local max and min and then absolute.
Mm-hmm. So that is best explained through pictures. So let's just do a little subsection here. We're going to do local versus oop, that's spelled wrong. Absolute. Okay. So when we are talking about a local min or max, the graph that usually comes to mind for me is something that kind of does this. We're looking at a continuous function that just kind of dips in the middle. Now here, looking at this dip, we would call this an absolute max, or local max, sorry, local max. And the reason why we say it's a local rather than an absolute is because, do you see this tail over here? It keeps going with values beyond this one.
Okay.
So when we're kind of talking about local, it's saying if you were to kind of cut this function off at some point, not look at values beyond a certain point, this would be the maximum value achieved. But we're looking at the entire graph. And so
Okay.
the local is saying that there are values past this one that are greater than this maximum. And same for here.
All right. So is it just kind of looking at like just like peaks and troughs in the graph, and those are just all local and max minimums?
Exactly.
Okay, and then the absolute is looking at like the actual max / min.
Yep. So that is when you're saying absolute, you were saying that there are no values greater than that. So like if you're looking at like a parabola kind of thing, this is an absolute maximum. Every value besides this one is less than it.
Okay, I think I got that.
Make a little bit more sense?
Yeah, for sure. I got that now.
Cool, cool. Any other conceptual questions you had?
Yeah, so I guess this is just more of very like clarification. So we use a sign chart on when we're just trying to find things that are increasing and decreasing. Just like where it's increasing and decreasing, right?
Yeah, so increasing or decreasing, or if you're looking concave up or down. Both of those.
Okay, yeah, that's on the second derivative though. I guess I was going to get to that. So f prime of x just with the sign chart, that's just increasing, decreasing.
Yep.
F double prime of x would be like the concavity of it. And then when we're looking at these absolutes with like intervals, we skip the sign chart and we just do like just kind of like a chart of like 1 is equal to 5, so on.
Yeah, when we have the intervals, we don't have to do a sign chart at all. We're just finding critical points and then plugging in endpoints. So you can just set up a table. You can just do it like how I did it, just writing all of that out. But yeah, you don't need a sign chart. You don't need second derivative tests, nothing like that. You're just looking for function values.
Okay, awesome.
The other thing I would say is even when you're looking outside of a closed interval, say an open interval, and you're looking for absolute extrema or even local extrema, you have a choice whether or not you want to use a sign chart or a second derivative test. It's kind of whatever you think is easier. We push the second derivative test because it uses a little bit more calculus knowledge. But you're really welcome to use either. So if you think the sign charts are easier to do than the second derivative test, absolutely do the sign charts. And especially since the test is going to be online, we're not really looking at your work. So it's however you want to go about solving the problem.
Okay.
I have some problems in mind that I could go over if you want me to. But
what time is
anything else? It is like not even 1:30, so we have a lot of time if you do have questions. Otherwise,
you just want to do like one of them? I don't want to hold you too long since it's only me.
No, that's okay. Well, and I was gonna say if you did want to head out, I'm more than happy to stick around, do some problems up, because I was gonna do some extra problems for the video that I was gonna post online. So if you don't want to stick around the whole time, I'm not going to hold you here, but I did have a couple problems that I wanted to go through, so you're welcome to stick around or not. Just let me know.
All right, I'll stick around for one.
Sounds good. Okay, so the one that I wanted to look at was problem 55. So we're looking at we're told that we want to find the absolute minimum on the interval 0 to infinity for the function f of x equals x plus 1 over x plus 30 over x cubed. Okay? So first and foremost, whenever we're talking about min or max, is always finding our critical points first. And one small thing that I'm going to note since we're dividing, oops, did not mean to zoom in. Since we're dividing here, we have to think about the fact that we can't divide by 0. So
yes,
x
that's
can't
undefined.
equal 0. But luckily, 0 is not included in our interval. So the function is defined for all values in the interval. Just a side thing to note. Okay. And then now we can go ahead and find our derivative. So we're going to have 1 plus, I'm going to write this as x to the negative 1 prime plus 30 x to the negative 3 prime. So we can break that step up a little bit. Okay. And then when we're taking x to the negative 1, we're taking that derivative. We should get a negative x to the negative 2. And then here, it'll be 30 times a negative 3, so negative 90, and then x to the negative 4th. And what I'm actually going to do is I'm going to rewrite that as fractions to make my life a little bit easier down the road. Okay. So now that we have that, we can just set this guy equal to 0 right away, because like we already said, we have to look out for when we're dividing by 0, but that's already excluded from our interval. So this derivative is never undefined in the interval 0 to infinity. It is undefined outside of that, but we're not concerned about what's going on outside. Okay, so as this function is written now, there's not a clear way to solve for it. But since we have now set the derivative actually equal to a value, we can manipulate this in any way we want. And the easiest thing to do would be to get rid of these denominators. And we can do that by just multiplying both sides by the largest denominator, which is x to the 4th. But anytime we multiply something by 0, we're just left with 0. So we still end up with something that's really nice to work with on the left-hand side. Ooh, that was bad. So then we get x to the 4th minus x squared minus 90. Now that looks a lot more like something we could work with because it kind of resembles a quadratic equation, something that's like ax squared plus bx plus c, but instead of x squared, we have x to the 4th and so on. But we actually can factor it the same way we would normally. So let's look at, hopefully this will make sense. If we do a u substitution here, and we just say u is equal to x squared. So we can rewrite this as u squared minus u minus 90 equals 0. We can do that. Doesn't change anything. How can we factor this guy? Because we know we can have u and u here. What are the factors of 90? What factors do you think we could multiply so that we get a negative 90, but add so we get a negative 1?
Hold on.
Yeah. Think of factors of 90 that are 1 apart. You know, like there's 45 and 2, but those are pretty far apart. What factors are really close to each other?
Gosh, I don't know. I'm blanking this one. I have no clue.
No, you're good. You're good. We can choose 9 and 10, right?
Oh, yeah.
They're only 1 apart from each other. So what we can do is we can have 1 be negative and 1 be positive. Which one do you think we want to be negative and which one positive? To
Negative
get a negative 1. Yep, exactly. A negative 10, positive 9. And all that's left is I'm just going to put everything back into terms of x squared. And we could have skipped all of that stuff. Actually, I'm going to do that in a different color. But I just think it's a nice way to think about it. Okay. So now we have something that's in a factored form that's really, really nice to solve for. So we can set each one of these equal to 0 and solve for them individually, which is just kind of nice. So let's go over here first. So we have x squared equals a -9. Can we ever take a real number, square it, and get a negative number?
No.
No. So we're going to ignore that guy. Oops, just going to cross it out. Over here, though, we get x squared equals 10. And that should give us how many options for x?
Plus or minus, so
Plus
2.
or minus, so 2, yep. Square root of 10. Awesome. And then now that we have our critical points, we need to look at our given interval up here. So we were told that x is in 0 to infinity, so therefore we're only going to look at the positive square root of 10. Cool. Okay, so now we have our critical point, so we can go ahead and either use a sign chart or use the second derivative test, but I'm going to use the second derivative test to kind of just reiterate how we go about it. So we're going to look at second derivative. I'm going to go back up to this guy, and I'm actually going to rewrite it back into this form to take the derivative. So we're going to go derivative of 1 minus x to the -2 minus 90 x to the -4. This guy will just go to 0, and then we should have 2x -3 plus 360 x to the -5. And then I'm going to rewrite that back into fractions for easier calculations. Because in my mind, it makes more sense to put it into a calculator in the fractional form rather than with the negative exponents, but very optional. Okay, and then all that we need to do for the second derivative test, which is why I really like it, is just plug in the number. There's no guessing and checking here. So, and we don't even really have to know what the number is. We just have to know if it's positive or negative, which is really, really nice. So, we are taking a positive number and cubing it. Is that going to be positive or negative?
Positive.
Positive. And then we're dividing it by a positive number, so that's still positive. I'm going to write that in a different color. Just for fun, and because I can. Okay, and then over here, again, we're taking a positive number to the 5th power. Is that going to be positive or negative?
Positive.
Positive, and we're dividing it by a positive number. So both of those are positive. So we don't even have to calculate what that number might be. We can already see that it's going to be greater than 0 because we have a positive plus a positive. Really, really nice. And when we're positive, we are smiling. So that is going to be an absolute min. So we can say our absolute min is f of square root of 10, and then whatever that number might be. Not too bad. Any questions about that problem?
No, I think I'm good. Thank you.
Awesome. Well, do you have any more questions for me?
No, I think I'm going to go take my quiz now. So, thank you.
You are good. You have a good rest of your day.
You too.
Okay, guys, so I think I might go through one additional question for you all if you do watch the videos, just because I want to make sure that all of the content is covered and hopefully I can get some questions out of the way. So a couple things that I would like to go over really, really briefly is when you are given an interval that is like 0 to infinity, where half of the interval is closed and the other half is open, that is still technically a closed interval. Doesn't seem like it would be because over here you have the infinity with the open interval, but it's still a closed interval. So actually, you can just use the regular closed interval test. You don't have to do second derivative test, sign chart, nothing like that. So anytime you see anything like that, just know you're still treating it like a closed interval. Okay. That was one of the main things I wanted to cover. The other thing that I wanted to go over, just as like a reiteration, really briefly, is when you are looking at something like e to the x or e to the negative x, remember that those functions, actually, we're gonna do it more like that. E to the x is always positive, which means it never crosses the x-axis. So e to the x and e to the negative x, for that reason, they are never equal to 0. So anytime you're dealing with a derivative where you have, say, e to the 3x, and you're trying to set that guy equal to 0, that can't happen. So if you have a derivative that's something like e to the 3x, e to the anything really, that has no critical points, okay? So when you are working with a function like that in a closed interval, all you're gonna do is test endpoints. You don't have any critical points to test. I think that was about it for that problem that I wanted to go over. Yeah, but I would say the only other things are, remember your derivative rules, and remember your second derivative test, because this is really just a reiteration of the second derivative test, keeping in mind the difference between how to find absolute extrema in a closed interval and how to find it in an open interval, and that you can only have absolute extrema in an open interval when you only have one critical point. Okay, so that is all that I really wanted to cover for you guys today. If you do have any more questions before you take your quiz, you're more than welcome to email me. But I hope you all have a good rest of your day.